Hi, my name is Abhinand and I'm representing team number 9. The title of our project is Machine Translation using Reinforcement Learning. First, let's define what machine translation is. So, machine translation is the task to automatically translate from one source language to a target language. Now, when we use deep neural networks to accomplish this task, it's called neural machine translation. NMT is formulated as a sequence to sequence task, and currently, transformer models achieve state of the art performance on this task. NMT models are usually evaluated using the BLUE score. It is calculated by comparing the n-grams in the generated text to those in the reference translation, and then computing the geometric mean of the precision scores for each n-gram. Now you may wonder, why do we need RL for this? Now there are a couple of reasons. Traditional NMT models suffer from two limitations. During training NMT models, teacher forcing is commonly used, but during testing, the model has to rely on its past outputs to generate predictions for the next time step. This leads to a bias in the model, which is called exposure bias. RL methods can help mitigate this issue. NMT models are usually trained using maximum likelihood estimation, but they are evaluated using discrete metrics like BLUE. This causes an inconsistency between evaluation and training. RL methods overcome this by allowing us to directly optimize the evaluation metrics. In our work, we mainly study three techniques to apply RL for neural machine translation, which are namely policy gradient, minimum risk training, and advantage actor critic. Policy gradient methods work by estimating the gradient of the expected reward with respect to the policy parameters, and then using this gradient to update the policy parameters in a way that increases the expected rewards. This is typically done using a variant of stochastic gradient descent. The main idea behind minimum risk training is to use evaluation metrics such as BLUE score as the loss function and directly optimize a model on it. In this approach, instead of maximizing the expected reward, we aim to minimize the expected risk of the model. In actor-critic methods, the actor and critic are both represented by neural networks. The actor network takes in a state and outputs a probability distribution over the possible actions. The critic network takes in a state and action pair and outputs a value function, which estimates the expected return from taking that action. In our project, we pre-train models before applying RL to fine-tune them and determine whether it can help. We conduct experiments on the German to English translation task. For policy gradient and minimum risk training, we utilize pre-trained transformer models. For actor critic, we employ traditional encoder-decoder RNN-based models with global attention. Based on our experiments, we observed that training NMT models from scratch using RL is not stable as the training diverges. However, if RL is used for fine-tuning a pre-trained model, we observe an improvement in the BLUE score. We can observe from the graphs of the validation BLUE score during training that both policy gradient and minimum risk training methods are able to improve the performance of the baseline NMT model by approximately 1 point. Another observation from our experiments is that minimum risk training is oftentimes more stable to train than policy gradient and actor critic methods. In conclusion, based on our experiments and the literature in this domain, RL indeed can be helpful in settings where it is used for fine-tuning of pre-trained baseline models. However, this improvement comes at a cost of longer training times and slow learning. In some situations, the improvement in performance is not significant and it is not worth the time it takes to achieve this. Apart from that, hyperparameter tuning is difficult due to the fact that there generally is a very high variance in the reward computation when training using reinforcement learning. In some cases, it might actually be better to use deeper models or ensembles to achieve a similar boost in performance. Thank you.